Working with vectors graphically. Here are a few principles to share. Number one, the location of a vector doesn't matter. Now here's that same vector v we were looking at. It's that 30 mile per hour northeast wind. I've drawn it here as a position vector, but if I moved it to another location in the xy plane, as long as it has the same length and the same direction, it's the same vector. There's no difference. Same length, same direction, same vector. Now, only that original one could be called a position vector, but the vector itself can be moved all around and it's exactly the same thing. Principle number two, you can multiply a vector by a scalar. Remember, a scalar is just a number. So using that same example, what if I wanted to draw vector 2v? Well, you can probably guess what's going to happen. Here's a picture of vector v. Vector 2v would be the same thing, only twice as long. So it heads in the same direction, it's just twice as long as it was before. Well, then what if I wanted to ask about the magnitude of vector 2v? Well, the magnitude of vector v, you remember, was 30, the 30 mile per hour wind. So the magnitude of vector 2v would be 60. It would be doubled. It would be twice as long. How about the direction angle for vector 2v? Well, it's pointing in exactly the same direction that vector v was, and so it would have the same angle. It was 225 degrees, this angle right here. Okay, let's try another one. What if we wanted to do vector negative v? In other words, -1 times v. Well, this time the length isn't going to change. Multiplying by 1 doesn't really do anything, but multiplying by that negative reverses the vector into the other direction. So when I multiply by a negative, the vector heads in the opposite direction. Here would be vector negative v. Well, let's list its features. What would be the length of vector negative v? Well, I didn't change the length, so it would still be 30, just like it was for regular vector v. Notice, though, that the direction angle has now changed. The direction angle runs from the positive x-axis to our vector, just in the normal way we've been measuring angles in trig. You can see there that this would be a 45-degree angle. So the direction angle for vector negative v is 45 degrees. So multiplying by a scalar can change the vector's length, and if it's a negative number, it can also reverse the direction. Principle number three, you can add two vectors together. Now let's say that I have vector A and I have here vector W. And I would like to draw on vector A plus W, which I could write like this or like this, same thing. Well, there are two different graphical approaches to adding vectors. The first one is called the tip-to-tail rule. And it goes like this. If you want to add vector A plus W, start at the beginning of vector A, go to its tip, and then pick up the next vector you want to add. Remember, you can move vectors around wherever you want. Pick it up and start it, put its tail where the other one ended off, copy the vector down. Well, the sum vector, otherwise known as the resultant vector, is the vector that starts at the very beginning where you started and ends at the very end. So this vector right here would be the vector A plus W. Again, you can call that the sum vector or the resultant vector. The other way that you can think of adding two vectors together is called the parallelogram rule. We're going to end up with the same answer. It's just a different way of thinking about it. In the parallelogram rule, you do not line up the vectors one after the other. You start both vectors at the same place, just like they're already shown. Now, notice that the two arrows here, if you think geometrically, they form two sides of a parallelogram. I'm going to go ahead and draw in dashed the other two sides by making a parallel line to vector A and then a parallel line to vector W. I've created here a parallelogram. To get the resultant vector, I start where the two vectors started, and then I move across the parallelogram to the opposite corner. You can see if you compare the pictures, I've drawn the same thing. This is also vector A plus W. Both the tip to tail rule and the parallelogram rule lead to that same resultant vector. By the way, in terms of application, perhaps vector A represents the speed and heading of an airplane, and vector W represents the speed and direction of an opposing wind. Well, the resultant vector shows what will actually happen to the airplane unless the pilot makes an adjustment. You can see in this example, it looks like the wind is slowing down the airplane a little bit. That red resultant vector is shorter than vector A. It's also slightly pushing it off course. These are some of the applications we'll see down the road. Thanks for watching.